Today, we are going to learn about the fundamental theorem of calculus, and it's going to allow us to answer some of these definite integral problems without looking at a picture, but understanding the picture will help you understand what this is actually doing. So, when we first learned about definite integrals, we looked at the example where we were given the rate of change function, kind of like velocity. And if you found the area under your velocity curve, you were actually calculating the distance traveled. So, what's another way of calculating distance traveled? Well, if you knew your location where you started, and you knew your location when you finished, and you subtract those two values, that gives you your total distance traveled. Okay? So, that's what this is. Okay? It's saying if you take the antiderivative of your function, in other words, you have your position function, and you plug your b in, which will give you your final location. You plug a in, which gives you your starting location, and you subtract those two values, it gives you your change in position, okay, or how far you have traveled. So that is the fundamental theorem of calculus. Let's go ahead and try to use it. So still in the box here in our notes, it says that let's try to integrate from 1 to 3 x to the third dx. Okay, so using the fundamental theorem of calculus, we are going to find the antiderivative of x to the third, which is 1/4 x to the fourth, technically plus c, right? We did antiderivatives, I said don't forget that constant. But what we're going to do is we're going to evaluate this, and here's the notation saying we now have our antiderivative, our integral symbol is gone, so this is the antiderivative function. We're going to evaluate it from 1 to 3. Well, that means using this theorem, we need to plug our 3 in, okay? So if we plug 3 in, we get 1/4, 3 to the fourth is 81, so let me just write that as 81/4 plus the constant. And then we subtract what we get when we plug our 1 in. If we plug a 1 in, we get 1/4 plus c. So in the description down there, it says, it is not necessary to include the constant c if you're evaluating a definite integral. Because look what happens when we do our work. C minus c, it's going to cancel each other out anyway. So we have 81/4 minus 1/4 is 80/4, which is 20. Okay? So we found the solution to this definite integral between 1 and 3 of the function x to the third. You do your antiderivative, plug your upper limit in, plug your lower limit in, and subtract those two answers. That is what that fundamental theorem allows us to do. Now we don't need the limit definition. We don't need to be able to use geometry formulas to find the area underneath this function. We now have a method of doing that. Okay? So the next page in our notes, a few more problems for us to practice. When we do a definite integral, you do not have to put plus c. If it's an indefinite integral, where you're actually coming up with the function and you're not evaluating it, you need your plus c. Okay? So understand the difference. Letter A on the next page. We are integrating from 1 to 2 x squared minus 3 dx. We're evaluating this definite integral. So my antiderivative is 1/3 x to the third minus 3x, evaluated from 1 to 2. You plug your 2 in first. That's like your final destination, okay? So you plug the upper limit in first. If you plug your 2 in, you get 8/3 minus 6. So that's the f of b part, okay? Minus, now we plug our 1 in. That's 1/3 minus 3, okay? So 8/3 minus 18/3 is negative 10/3, minus 1/3 minus 9/3 is negative 8/3. So negative 10/3 plus 8/3 is negative 2/3. Okay? So getting a negative response, what mentally, okay, what does that mean about this function? All that means is that more of that graph was below the x-axis. Okay? That's why our net answer ended up being a negative number. So we still need to conceptualize what's happening there. Okay? That means between 1 and 2, it actually went backwards overall. Might have went forward a little bit, but that net change is from where it started, it's behind by 2/3. Okay, next example, letter B. Letter B, we have the integral from 1 to 4 of 3x to the 1/2 dx. So put it in a form that you know how to find the antiderivative. All we know is the power rule right now, or if it's a specific trig pattern, okay? So the antiderivative, we increase our exponent by 1, it's now x to the 3/2. We divide by the 3/2, or multiply by 2/3, and we're evaluating from 1 to 4. Okay? We plug our 4 in. Now, to the 3/2 power means it's a square root being cubed. Okay, the denominator means the radical, square root, and then we can cube that. So when we plug a 4 in, it actually is 2 to the 3rd, which is 8, times 2 is 16. Minus, then we plug our 1 in, get 2. Final answer is 14 for that problem. Okay, and then like I said, for the only integration problems we know how to do until we get to chapter 5, the only ones we know how to do are power rule problems or specific trig problems. So we have the integral from 0 to pi over 4 of secant squared of x dx. Well, I know that the derivative of tangent is secant squared of x. So the antiderivative of secant squared is tangent of x. We're evaluating from 0 to pi over 4. We plug our pi over 4 in first. Tangent of pi over 4 is 1. Minus, we plug our 0 in. Tangent of 0 is 0. So we get 1 as our answer. So that is using the fundamental theorem of calculus to evaluate, technically finding the areas underneath these functions, or between the function and the x-axis, over the given interval. Okay? All right, I do want to go over the next 2 examples, the 2 main examples, okay? And then we'll be done for today. So it won't be too bad, hopefully. The next ones are these absolute value problems. We do not know how to find the antiderivative of an absolute value. I can't find the derivative of an absolute value unless I get rid of the absolute value symbol. And we can do that by doing a piecewise function. Okay? So that's how we're going to have to handle letter A and letter B under this next example. We're supposed to integrate from 0 to 2 the absolute value of 2x minus 1. So we need to split this because technically it's like 2 lines. Think about an absolute value graph, right? We have these 2 lines and we want to find the area under one and the area under the other one. We technically could use geometry for this if we wanted to, but I'm going to use the calculus instead. Now I know that the vertex occurs when this absolute value is equal to 0, which is at 1/2. So I'm going to split this integral to go from 0 to 1/2 plus 1/2 to 2. I have to split it where that vertex is. That's when it changes from this line to this line. Okay, if I plug something between 0 and 1/2 into this function, like 1/4, 2 times 1/4 is 1/2, minus 1 is negative 1/2. I would have to do the opposite to get the correct answer there. So that helps me understand that I actually need to do the opposite of the 2x minus 1. So the opposite of that, that's the first integral. That's actually the line without my absolute value in there. Over here, if I plug like a 1 in there, the absolute value symbol is irrelevant. So this is really just 2x minus 1. So those are my 2 halves I got to figure out. Using my second fundamental theorem, all I have to do now is the antiderivative evaluated at these spots. So this first one is going to be negative x squared plus x from 0 to 1/2. Over here, this is going to be x squared minus x from 1/2 to 2. And I put this front bracket on there just because I was adding. I wanted to show you this is the separate piece. If it's just that, you don't need to put that front bracket on for notation purposes, okay? Now right here, if we plug a 1/2 in, we get negative 1/4 plus 1/2 minus, if you plug a 0 in, you get 0, okay? So that's the upper one minus the lower one. Plus, evaluating this, we got our upper one, which is 4 minus 2, minus our lower one, which is 1/4 minus 1/2. So all of this together will be the answer to this original problem. This is a positive 1/4 plus 2 minus, let's see, 1/4 minus 2, that's negative 1/4, so minus negative 1/4. So we get 2.5. Okay, so using calculus, that's our answer. What if we didn't want to use calculus, or we forgot? Or we want to check our answer because we have time, possibly, right? I could graph 2x minus 1. If I plug 1/2 in, I get 0. Plug 0 in, I get 1. Plug 1 in, I get 1. Plug 2 in, I get 3. So I could find the areas, the area right here. Well, that's 1/2 times 1 is 1/2 times 1/2 is 1/4. Boom, that's the area of the first piece. Okay, the next piece, this is 1.5 times 3. Okay, so 3/2 times 3 is 9/2. Half of that is 9/4. So 9/4 or 2 1/4. There's my 2 1/4. Okay, so you see that each integration piece does actually calculate the area underneath both sides without actually doing the graphing. And we end up with our final answer by adding those two areas together. We split it, we added both of them together. Okay, so letter B. I'm not going to sketch this one out, but we're going to try this one. This one's integrating from 3 to 6. 4 minus the absolute value of x minus 4 dx. All right, so I know that the vertex is going to be at 4. Okay, it's when this absolute value is equal to 0. So I know it's going to occur at 4, which means this needs split at the 4. Okay, so that's my setup. I need to split it at the 4, but if I add the first piece and the second piece together, I really have that whole piece. That's one of the properties, right? So think about what we need to do the opposite for. Okay, so if I plug 3.5 in here, or even if I plug 3 in here, I get a negative 1. So I have to do the opposite of what's inside. So that problem is really 4 minus the opposite of x minus 4. That's really what that means. Take the opposite of the inside. The opposite of the inside, and I have to subtract that. Over here, if I plug a 5 in here, the absolute value symbols are irrelevant. So that's really 4 minus the x minus 4, whatever I would get there. Okay, so let's simplify both of these. This first one, it's 4 plus x minus 4, that's just x. That integral is going to be fairly easy. Okay, over here, the integral from 4 to 6, that's going to be 4 minus x plus 4, so that's 8 minus x. Okay, so this one ends up being 1/2 x squared. We're going to evaluate that one from 3 to 4. And then this one ends up being 8x minus 1/2 x squared. That's from 4 to 6. Okay, so right here we need to plug our 4 in first. That's 16 times 1/2, that's 8. Minus, then we plug our 3 in, and we get 9/2. So just this first piece, we have 16/2 minus 9/2 is 7/2. Okay, that other piece, we plug our 6 in. We use parentheses because I got two things to put when I put my 6 in there. I have 48 minus 18. That's what I get when I plug 6 in. minus, now I plug my 4 in. That's 32 minus 8. Okay, so that's going to be 30 minus 24, which is 6. We add both of those together, so 12 halves plus 7 halves is 19 halves. And that's what I got here, so that's 19 halves. Final answer, all together. Okay, last topic gets into a very small instruction word, okay? So you gotta pay attention to the question. This next one says, what is the difference between just integrating over a specific integral or finding the total area or total distance traveled instead of the net change in distance? Okay? Like for example, if I run to the door and back, integration would tell me that I've traveled 0. Whereas if I wanted to calculate the actual total area or total distance traveled, I would add that first one and add the second one separately. Okay? Add the part that was positive and make the part that was negative positive and add that together. So that's the idea of the difference between these two problems. So letter A, we are supposed to integrate between 0 and 6 the function x minus 3x squared. So if it just says to integrate, you don't really have to worry about what the function looks like. You can just go ahead and do the problem. So that is going to be 1/2 x squared minus x to the third evaluated from 0 to 6. So we plug our 6 in. That's 18 minus, what's that, 216? Minus 216. So we end up with negative 198. That's the answer, if it says to integrate. Now, if it says total area, or total distance traveled, not just the net change from your starting position, now you have to think about where that function crosses the x-axis. You want to think about what's above, what's below the x-axis. So if I would do letter B, I would want to see what this function looks like. So for instance, I might just plug 0, 1 through 6 in. So 0, if I plug 0 into my function, I get 0. If I plug 1 into the function, I end up with negative 2. If I plug 2 into the function, I get 2 minus 12, I get negative 10. It's going to go way down there. All right, well, what else do I know here? I know that for this function, just trying to give you guys some techniques when you're looking at this, right? You know how to curve sketch. Some important points are where it crosses the x-axis. That's really what we need here, okay? I want to know, where does it cross the x-axis? When's it equal to 0? Because that's when it actually changes from above to below the x-axis. Those are important points. So if I factor an x out, I get 1 minus 3x. So I get x equals 0. And this one I get x equals 1/3. So actually at 1/3 it crosses the x-axis. It actually goes up first, and then it comes down and goes down the rest of the time. So total area would actually be this little section here plus the absolute value. That's that that's 1, 2, 3, 4, 5, 6. All of that. All of that actually through integration would be counted as negative. I'm just going to take the absolute value of that and add that to that area there. So here's what it should look like. The integral from 0 to 1/3 of this function, x minus 3x squared, plus the integral from 1/3 to 6 of this x minus 3x squared dx. Now technically you just want the absolute value of each piece, okay? You want the absolute value. You want it to be a positive area. Now I know that that's the one that I'm going to have to change the sign of. This should be a positive number because I know what it looks like. But if you don't know whether it's going to be positive or negative, just make sure you take the absolute value of the pieces, okay? So this problem, we already have our antiderivative, but we could do it again. It's not a difficult one. We're going to evaluate that from 0 to 1/3. So we plug 1/3 in. 1/3 squared is 1/9 times 1/2 is 1/18 minus 1/27. And that's what I get when I plug 1/3 in. Minus, then I plug 0 in, which gives me a 0. Think through that though, because plugging 0 in doesn't always give us 0, so don't get caught on the fact that it gives you 0 most of the time. So 1/18 minus 1/27, that ends up being 1/54 if you get a common denominator. That's 3/54 minus 2/54 is 1/54. So that's actually the portion that is that little positive area. It's like I'm going to go forward a little bit, and then I'm going to go backwards the rest of the time. This is the backwards part, okay? So when we evaluate this integral, we end up with 1/2 x squared minus x to the third evaluated from 1/3 to 6. So we plug our 6 in, we get 18 minus 216 minus, then we plug our 1/3 in, which is 1/54. So that ends up being negative 198 and 1/54. So that's how much was backwards. I'm going to make that positive. Absolute value. And add these two areas together. I get 198 and 2/54, or 198 and 1/27 would be the total area. Okay? So in other words, here's my starting position. This integration tells me that when all of this is said and done, between now and after 6 units, I would be backwards 198 units. This question is saying, well, how far did you actually go? I went forward a little bit, and then I went backward, and I ended up 198 from where I started, but I actually traveled 198 and 1/27. So pay attention to the question to know whether you need to do your splitting. If it's just an integration, those are the easier ones, okay? And that is good enough for today. And you guys have a homework assignment to practice this fundamental theorem of calculus. Bring your questions to any classes that you attend, and I can address them then. Take care.